Good afternoon, Fancy Meat Computers. Sorry about the links. Hey. I didn't get a lot of sleep last night. Yeah, we did this. There we go. Nah. Yeah. Oh, I don't know. I think I probably, I think I definitely have worked harder this semester than I ever did when I was an undergraduate. But, you know, time, the mists of time sort of swirl on, you know. How many people we got? There we go. 9 people in the class. 7 of them having voted. Most of the people in attendance aren't actually in attendance. Physically or virtually, but perhaps not spiritually. Something like that. That's too much information. Good Lord. So, there we go. 13 people. That's good enough. So, might as well get started with then. Yep. Oh, I suppose I should talk about Project 3, huh? So, Project 3 was released over the weekend. So, probably it would be useful to talk about it for a tick before we get to our lecture today. So, essentially, Project 3 is a combination of a bunch of different things. Why is Project 3? Because that's tautological. It is because it is. So, Project 3 is essentially very similar, very much in the vein of Project 1 and 2. Project 3, however, requires a bunch more constructs that we've covered at various points throughout the course. Primarily focusing, of course, on the stuff that has occurred since Project 2. And essentially, you need to take the work that you did for projects 1 and 2, combine that with a type checker, then add in unit let bindings, the sequencing operator, and reference values, and do type checking for all of those as well. And that's project 3, essentially. All of the relevant semantic rules have been copied into the project document, so they're handy for your reference. It's going to require a certain amount of correct intuition with respect to how to bridge the gap with respect to substitution, for example. In essence, remember that let bindings are essentially lambda abstractions, and that should guide, and everything else is just a regular thing. So there you go. Oh, come on, you guys love the projects. You love doing actual coding. And do it with no time, since your other courses are likely time whores. Yes. Indeed. So let me explain then the... so I've taken this idea into account, actually. So let me talk a little bit about the scoring, because, like, I understand that this is, like, as a project, this is, like, maybe, you know... This is a fair amount more work than either of the preceding projects was. So let me explain how the scoring is going to go. Alright? Essentially, you're going to be scored on the feature set that you can get working, right? Now, the feature sets have to be cumulative, right? So you're not allowed to skip any feature as you're going through the project and implementing features. So this is kind of suggesting a design, like a software design process to you. If you want to sort of maximize the number of marks that are in your project over time, start with the Booleans, then do the naturals, then do lambda calculus, then do the unit type, then let bindings, sequencing, and then references as the final step. So the total number of marks available through all of this is 110 out of 100, so there are 10 bonus marks available. Maximum score is 110%. You'll notice that you can get as far as sequencing and still get 90%. So essentially, to get an A, you do not need to do the referencing portion. And it says this rather, like, kind of explicitly in the project layout itself. It's like, it's very explicit about saying, listen, you can get an A+ on this without doing this section. But if you want a shot at the bonus grades, you're going to do this section as well. So there's, as you can tell, like, Booleans, naturals, and lambda calculus are all things that I've asked you to use before, or asked you to implement the semantics for in the past. I've provided you guys with the data types this time, which I would like you to use. So basically, you get like 2, 2, and 4 marks for taking your old project 1 and 2 your old project 1 and 2 implementations and converting them to the new data types. So, you know, a little bit of a freebie, to be honest with you. All you have to do is some renaming. So most of these first bits are going to be the implementation of a type checker over Booleans, naturals, and lambda calculus. So it's like you can get as far as 30% without having to worry about gamma, but in order to pass, you need to do work with gamma. The unit type is practically a free 5% because it's like one typing rule and that's it, right? Most of the work having to do with unit is like built into the data types that you're already given, so you don't, that's it. That's all she wrote. Let bindings and sequencing operators, like, it's kind of like getting yourself to 55% is like probably the biggest task. After that, you should be able to get yourself from 50%, 55 or 60% to 90% relatively quickly. But I'm not going to lie, referencing is difficult to get working. I've even included, like, difficulty ratings on each of the questions, a la the textbook. So that sort of gives you an idea. Perhaps you can better plan your time. But yeah, so that's the project. Any questions about the project? I would love it if 3SD3 wasn't due a day before. Yeah. Did I put the due date on Avenue? That's a good question. I think I did. I think that was my, like, triumphant pressing of the Enter key at the end of it. Let's see. Should be the last day of class. December 8th. Yes. Wow, we've already got one submission? That's impossible. Come on. Well, I'm not going to do that on stream. But that's interesting. Someone finished the project already, guys. Lord have mercy on our souls. No! Feudalism won't save you here. Oof. I think it was religion, not feudalism, that he was referring to. But I see the joke. In general, as a system of government, feudalism, underrated. Watch the submission of someone sending a picture of a cat just saying, please. Actually, it's a Haskell source file. So, chop chop, everyone. If I may make a recommendation, probably the best way to handle this one is to not procrastinate and leave it all to the last. It is a bit sus, isn't it? That is a paid actor. Well, come on, I posted it. Let's see, what time? I posted this at like 11 p.m. Saturday night. It's now after 12 on Tuesday, so that's Sunday, Monday, half a Tuesday, so 2.5 days. That's your, you know, it should take you no longer than 2.5 days, I guess. Oh, I meant the feudalism comment was sus. Oh, really? No? Yeah? I mean, look at it this way. Life was simpler back then. You didn't have to, like, spend so much time agonizing over what profession you were going into because you just do the one that your dad was in, you know? Sure, you know, you live the life of a dirty peasant, but you get to drink beer instead of water, right? All the time. You know, you don't have to worry about grades or school or careers or trying to sell your soul to a corporation, trying to convince a corporation that your soul is sufficiently dead already that corporation would want you working for it. No, all you really have to worry about is if the barley crop turns out, you know? That must be Marty McFly. He has an advantage. Yeah. Yeah, I'm all about feudalism. You know, people under feudalism, like a blacksmith in the feudal age got like 200 days a year off. Like, he only worked like 150 days out of the year. your average village blacksmith. Take that, put that in your capitalist pipe and smoke it. Anyway, so that's Project 3. I am assuming everybody's just completely blown away by the magnitude of my genius putting this project together. That's why there are no questions. As usual, if you have any questions, post them to the forum. Who said anything about capitalism? Well, capitalism at least works. Unlike certain other things that think that capitalism isn't good. So, anyway. You know the term capitalism was invented by communists? Anyway. So let's talk, let's continue on. Let's actually do some actual lecture material today, shall we? So, we're going to talk about normalization. We're doing chapter 12 in the textbook, so this is a very interesting and important result. We're going to revisit some items that we talked about in topic 6. So, normalization. What is normalization? Normalization is the property of normalizing. That is to say, the property of evaluating to a normal form. That is to say, the property of terminating. So, essentially, we're kind of in this cozy little in-between space in the textbook between, like, advanced type systems we're not going to cover in this class, and the type system that we've developed so far, and, like, at the present moment, with the constructs we currently have, we can actually do a proof of termination for well-typed terms of the language, which is kind of cool, because pure lambda calculus does not necessarily terminate because of the existence of things like the omega function. So that's what this is going to be about. So, normalization. Over the past month, we have examined simple types in detail. We have We have demonstrated that type systems can help us avoid executing terms containing semantic errors. There is one important property that we haven't touched on yet, which we touched on in our previous discussion of untyped lambda calculus, the halting problem. Just to recap, the halting problem, informally stated, is, will a finite program terminate in finite time? This can also be stated, can an algorithm be written which determines whether or not other algorithms terminate? Generally speaking, the agreement among computer scientists, which is backed up by theoretical results, is that the halting problem is undecidable for Turing-complete languages. So, given that, in our lambda calculus, it is impossible for us to type terms which result in infinite recursion, when we talk about the subset of the language that is well-typed, that is no longer Turing complete, right? We lack the ability to perform infinite recursion, or, basically you don't have Turing completeness unless you can get it stuck in an infinite loop. And since since infinite recursion can't occur because we can't type the fixed point operator or we can't type the omega function, the well-typed portion of the language can be proved to terminate, which is kind of cool because termination is a very, very important property. So, the object of this lesson is to use our type system to make the halting problem decidable for well-typed terms of our calculus so far. So, here is a quick recap of the idea of Turing completeness or equivalence. To review, a system of computation is considered Turing complete or Turing equivalent if it can perform all the actions of a Turing machine. The minimal set of things you need to be able to do is A. Support conditional branching. This implies support for arbitrary go-to operations. And B. An infinite amount of tape or memory. Technically speaking, no physical computer can be Turing complete because of the physical constraints on memory. The Church-Turing thesis states that a function on natural numbers can be calculated by an effective method if and only if it is computable by a Turing machine. A secondary effect of the Church-Turing thesis is that a program is computable via a Turing machine if and only if it is computable by a lambda expression. So that's a pretty important result when you're trying to determine what can and cannot be computed. Simply typed lambda calculus is Turing complete because we can construct infinite lambda expressions which have infinite evaluation chains. Where most languages achieve this with loops, lambda calculus and Haskell achieve this through infinite recursion. So, let us reconsider the omega function. During a previous assignment, you were asked to reason whether or not the omega function is well typed. Just to remind you, this is what the omega function looks like. It's two terms. The two terms are the same, and you apply the one term to the other. Essentially, this is applying a term to itself. The term itself is lambda x, x applied to x. So, as previously demonstrated, every time you evaluate the omega function, you get the omega function back. So it's an infinite loop. It will result in an infinite chain of evaluations which never terminate because you always get back the thing you put in. So, let's try typing the omega function and see how far we get. First, let's assume that there is some type t such that the x in the lambda abstraction has that type. It should be obvious, first of all, that these two t's are the same t. Otherwise, how would it perfectly replicate itself? It wouldn't be able to, right? In order to perfectly replicate itself, it would need to also replicate the typing. So, first, it should be obvious that the types of the two abstractions must be the same, otherwise the function would not be replicating itself perfectly, as I just said. Let's consider the application of x to x inside the first lambda abstraction. In order for this application to be well typed, the first x must have type t yields t. Is there more to this argument? I feel like I've lost some... Did I have a rendering issue? Pardon me, guys. Sorry. Just give me a moment to check the source. I feel like a point got cut off. Maybe I'm just paranoid. I think I might just be paranoid. There is more to it. What the heck, man? Great. I can't fix that at the moment, so I'll just... Right. So, the bit that got cut off of the slide is that we know that the type of both x variables is t, right? So, essentially, overfilled VBox. See, it's the spacing, right? If I just... Here, let me... It technically doesn't give you a... In Beamer, it doesn't give you a overfilled VBox warning. It just cuts it off. At least I think so. Oh, it does actually. Okay. Let's see. Give it another 0.5. There. Good. That's everything. So, right. So, in order for this application to be well typed, the first x must have type t yields t. We know that the type of both x variables is t, however, and t cannot equal t yields t. We have a logical contradiction, so the expression must be untypable. So this, I expect to be a fairly controversial way of approaching it because, you know, there's a counter-argument to this. But what about infinity? So the counter-argument is that if t is an infinite chain of types linked by the arrow type operator, then in theory we could do something like this, right? So if we say that t is some s infinitely with an infinite chain of s types, right? Yeah. So see? Yeah. So if t is some other type s, which is an infinite chain of s's, right? Then if you substitute s for each of these t's, right, in t yields t equals t, then what you get is t infinitely yields s, s infinitely yields s, which yields s, which yields s infinitely, an infinite number of times. On the one side, you've got two infinities plus another one. On the other side, you have one infinity. So can't you just collapse all of those together and say this is equal, right? Can't you just say that? So doesn't that make this typable? So here's the counter argument. To show why this is not the case, we must ask ourselves how equality is defined over the cardinality of infinite sets. Which is, you know, I had to go look it up. I didn't know this before I looked it up. So, it turns out two infinite sets have the same size and are therefore equal, at least in terms of cardinality, if a one-to-one relation can be constructed between them. That's how they define equality over sets of infinite cardinality. So, in this case, let's consider the types in t yields t to be A, and the set of types in t to be B, right? According to the original definition, no matter how many types are in B, A will always contain at least one more, right? These extra elements can't be pointed to by B. You would need to be adding elements to B at the same rate as you add them to A for it to be equivalent. Therefore, the contradiction holds and the expression is untypable. There you go. Any questions? I'm expecting everybody to jump into the chat with like, but what about this? But what about that? But maybe there's not enough collective will in the chat to be able to fight me on this one. But you know, it's like it should be clear that A is growing faster than B, right? Like, it always contains at least one more element, no matter how big it is. Even if it's not infinity, it'll always contain at least one more element. Nobody gonna fight me? Your expectation is on a faulty assumption. We still have the will to live and participate. Okay, well, if nobody wants to fight me on it, then we'll just move on. But that's, so, like, the reason this doesn't work is, like, what is meant by equality, right? Anyway, so let's move on to the idea of term normalization. A term is said to normalize if it reaches a normal form through a finite number of execution steps. The goal of this lesson is to demonstrate that all well-typed terms are normalizing. As we will see, normalization holds for the simply typed language we have built so far, but once we add loops or general recursion, this property will no longer hold. Well, if we were to add loops or general recursion, because we're not going to do that in this class. Basically, next week and at the end of this week, because normalization is going to take us 2 lectures, not 3, we're going to be talking about errors and error handling, and we'll have covered the entirety of parts 1 and 2 of Pierce, except for a few bits in the middle. Aren't both of them still countably infinite? And? It depends on how you want to define the infinity, I suppose. Personally, I think it makes more sense to use the set definition, since we've been using set theory all along here. So, a term is said to the goal of this lesson is to demonstrate all well-typed terms are normalizing. As we will see, normalization holds for the simply typed language we have built so far, but once we add loops or general recursion, the introduction of recursive types would also destabilize normalization. Are we still in testable content because this is way harder to take notes for than the earlier stuff? Thank you, Mark, for presenting me with the professor's dilemma. If I say this is testable, everybody's anxiety goes through the roof. If I say this is not testable, everybody leaves. I haven't written the exam yet, so it's kind of Schrodinger's topic. It is both on the test and not on the test until you see the test. And I realize that's not helpful. But yeah. Also, we still got a good 2 weeks of class left. I gotta, it's too early to stop teaching you testable content. So, problems with proof by induction. Throughout the course, we have relied heavily on proof by structural induction over terms. There are some drawbacks, however, to this technique. It can be difficult to find the right induction hypothesis, as the evaluation of a program may not preserve the structure of the terms. Our induction hypothesis are... Now I lost my train of thought. 3DB has finished teaching testable content and is just doing review sessions and bonus stuff. This is karma for doxing. Who did I dox? I didn't dox anyone. What? My God. I don't understand my relationship to the karma in this case. Am I the person who's experiencing the karma, or am I the person, subjecting you to the karma? At any rate. Oh, okay. Mark is the one experiencing the karma. Okay, good. As long as it's not me. I've tried to keep my karma clean, but it's difficult when part of your job is to, enforce pain and misery. Oh, okay. What? Are you saying that that's not that person's real name? Yeah. Alright. Anyway. 3DB can handle itself how it likes. I'm going to run my course the way I want. Boom. So anyway, so a lot of the time we've been doing proof by induction, right? And that induction has been specifically on a server where it wasn't Node. Yeah, okay, Mark, that's... Okay, so to Lunari, I would say I wouldn't call that full-blown doxing, you know? Doxing is usually like also doing the address and that kind of thing. But Mark, that's still like, you should know better, man. You should know better. Yeah. Okay, I'm not... Okay. Shut up, you two. This is not the time or the place. This is not the time or the place. So, in fact, I'm just gonna hide you two until you're finished with your little lovers' quarrel. So, proof by... so, we've been using proof over structural induction quite a bit in this course. When you take a term and you prove something about... If you're trying to prove something about a term, you assume it's true for the subterms, and that allows you a hypothesis to conclude whether or not it's true for the term in total. It can be difficult, however, to find the right induction hypothesis, as the evaluation of a program may not preserve the structure of the terms, particularly once you introduce lambda calculus. Consider the term T1, T2, that is, T2 applied to T1. Our induction hypothesis might state something like, all subterms have some property. If the above application results in a substitution, such as x gets substituted for s in T2, our induction hypothesis says nothing about whether or not that property is preserved under substitution. In the past, when proving properties like the preservation of well-typedness under evaluation, we have introduced lemmas proving preservation under substitution as well. That's the reason, right, that we've needed to have substitution lemmas in addition to, like, preservation properties when we've proved things in the past, is because, you know, essentially we have two semantics running in parallel, right? We have the, well, three if you count relabeling, right? You've got the essential evaluation semantic, which is all of the rules we've been doing, the substitution semantic, which hopefully is simpler, and the relabeling semantic, which is also simpler. So, the proofs of normalization we will cover in this lesson rely on a new proof technique called proof by logical relations. Proof by logical relations are so called because they preserve the property of interest across logical implication, i.e. functions. Due to the Curry-Howard correspondence, this is applicable to typing as well. So, essentially the entire point of this, like the point of doing the normalization proof with you guys, is to expose you guys to a new proof technique, which, you know, probably I won't require you to produce this proof technique on the exam or anything. It's just, you know, you should see it because it exists. So, let's set up our proof technique. We wish to demonstrate the normalization property of simply typed lambda calculus. For this proof, we will consider only the lambda calculus terms themselves, that is, application, abstraction, and variables, augmented with a base type A. We begin by defining each type T. By defining for each type T a set RT, which contains all the closed terms of type T. So, there are going to be a few definitions you have to, like, cast your brain into the past. Yay, I'm here, but 39 minutes in the past. Well, get with the program, man. It'll be fun in 39 minutes from now when this person sees that. Anyway, so there are going to be a few definitions from earlier in the course that you're going to have to recall in order for this to make any sense whatsoever. Number one is the difference between closed and open terms, right? So, a closed term is a term which contains no free variables. And a term which is open is one which contains free variables. So, this is like a subset of the different types of terms that we're talking about, right? So, number one, for us to be concerned about it, the term has to be well typed. And number two, it also has to be closed. Although, as we're going to see, the fact that it's typed also means that it's closed. So, remember the difference between free and bound variables, right? So, a free variable is one that is not bound by any lambda abstraction, but a bound variable is one that is bound by a lambda abstraction. So, for example, if we have lambda x, xy, x is a bound variable, y is a free variable, this on its own is not in our set R that we're defining because it contains a free variable. However, if we expanded the thing to look like this, that now counts because both x and y are bound, so this is now a closed term. So there we go. So, so this is like a just a slight sort of syntactic point. Since this is a set, which is a it's a perfect subset, or it's a subset of the set of terms. So any subset of a set you can regard as a predicate over that set. So you'll often see in this proof RT of T to mean T is an element of RT. So please just put that one in your brain. So let's define RT more formally. Essentially, we have two cases. In the case of the type A, R of A, if T is in RA, then it halts, and vice versa, right? Halting and normalizing is the same thing. If, however, we have the set of closed terms of types T1 yields T2, if T halts and we have some S such that it is in the set of closed terms of T1, then we know that T with S applied is in the set of closed terms of type T2. Note that in this case, note that this is in essence a case analysis over the valid forms of T. So we have a particular type of set R for type A and a particular set R for type T1 yields T2. The first case straightforwardly states if a term is well typed, that term that type is a base type, the term also halts, and vice versa. So the bidirectional implication here is going to be important. Incidentally, we are defining these sets this way. This is a definition, not like we're not going to prove this, right? We are saying this is the case. This is how we're defining. This is how we're defining it. The second case is a bit more of a mouthful. So, if T is in the set of closed terms of type T1 yields T2, we know that T must be a lambda function, because lambda functions are the only things that can be typed with the arrow type constructor. It is not sufficient to know that this function itself halts. It is a value, so it halts trivially, right? There's no point in determining that it halts. It already halts because it's a value. Applying terms to lambda abstractions can increase the number of readexes in the expression. as with the omega function. Therefore, we must additionally know that if we apply some halting term s, any halting term s, which has type t1, the application of this term to t must also halt under t2. This, the way we've designed this, the typing will always work out correctly, but so the idea is it's not sufficient to know that the lambda abstraction itself can't be evaluated into anything, because of course it can't be, it's a value. What we're interested in is, does this lambda expression cause anything to explode, right? So what we do is we declare the metavariable s to stand in for literally any term, right? So that's how this proceeds. In this case, proof by logical relations is a form of induction over types. If we wish to show that some property P holds for all well-typed terms, we start by demonstrating that all terms of type A possess property P. Then we want to prove that all terms of type A yields A preserve the property P. Then we also want to prove that all terms of type A yields A yields A, and we want that to preserve the property of preserving the property of P, etc., etc., etc. Right? In essence, we want to define a family of predicates indexed by types. I just realized I'm going pretty fast. So I'd like to pause for questions. Questions? Okay. Well, there's one person with a question. I will hear your question. What's a redex? Oh! That's an easy question. A reducible expression. So, so the idea is that when you perform a substitution over a lambda operation, that can result in there being a greater total of reducible expressions. That is, like, a greater number of latent applications of EAPS abs inside of the term than when you started, right? And in fact, just because this is the way lambda calculus works, you can't, like, essentially the point here is that you can't just, like, make a argument, you can't just make an analogous argument to the way that we proved termination over UAE, right? The way that we proved termination over UAE is essentially to say that the size of any term must be reduced through evaluation, so it's in some way mappable to a well-founded set that must eventually reduce all the way to 0, so everything terminates eventually. That's our argument for UAE, right? Because lambda expressions may introduce additional reducible expressions, that is, additional redexes, you cannot make a similar argument, right? The number of reductions may increase and then gradually and then decrease later. It may decrease now and increase later. Essentially, you can no longer map the number of redexes to the natural numbers because it may increase or decrease. So you can no longer make the argument that the number of redexes is a well-founded set, so by eliminating redexes you would eventually reduce the term to a value, which is, true. That's why pure lambda calculus, untyped lambda calculus, is there's no termination property for it, which is why we get the omega function. So in this case, essentially, we're trying to get around the fact that the number of redexes may increase, but so long as the result of the application is still inside of this set that we've defined, we know that it'll still terminate. So that's essentially the gist of what we're trying to prove. Could I please go over that again with the A? Yeah. Okay. So yeah. So proof by logical relation. What we're trying to prove here is that some property P holds for all well-typed terms. Yes. Following Church, a term of the form... yes, yeah. Correct. Yeah. Yeah, that's the formal definition of a redex in the chat there. So, we start by demonstrating that all terms of type A possess property P. We then want to prove that all terms of type A yield A preserve property P. So essentially, think about the set for our base type, right? Think of R sub A, right? R is the property, A is the type, right? So we have that type. We now want to say that, like, A yields A would also preserve that type, right? So, or preserve that property. So the idea is, if you have a thing that is typed A yields A, you put something A into it that is closed, do you get something closed out of it? And, and then, of course, like, you just continue to increase the number of abstractions, the number of layers deep the arrow goes. You want to demonstrate that you preserve the property over, like, expressions of increasing type complexity, right? So, in essence, what you want to do is you want to do an inductive argument where A is the base case and T1 yields T2 is the inductive case. If you can demonstrate that if, like, T1 has the property, that means T2 must have the property via T1 yielding T2, that is preservation of the property, right? And if that property happens to be the property of termination, then we have proven termination. So this is the essence of the proof by logical relations. Any more questions? It's a private question. Between undergraduate life and doctoral life, which one was harder for you? So it's like, you can't really answer that question without it being like a personal, like, I have to talk about me as I answer that question. So whether or not what I'm about to say generalizes to any of you, that's like, maybe it probably won't, but this is in my experience. So my undergraduate degree was a lot of work, and an undergraduate degree is a lot of work in general. In general, when you get to grad school, the courses are easier because there are far fewer of them. Like, they do expect a lot more out of you, but you, generally speaking, only take 2 per semester. So while they are a lot harder, they're you actually have the time to study them properly. So that's one of the differences between grad school and your undergraduate degree. However, if you're a person such as myself, who has, you know, I took 2 rounds of grad level courses. The first during the first year of my master's degree, and that I ended up transferring to the PhD program and not getting, and then one in the first year of my PhD studies. So I ended up doing 2 rounds through grad classes. And I prefer taking courses at the graduate level to taking courses at the undergraduate level. You just get to study the concepts in more depth, which is what I enjoyed that about it, because, you know, it's kind of like less frantic, shall we say. The killer is what comes after the coursework in grad school. So personally, I have a personality that, like, I thrive in an environment with more external structure, right? So I guess you could call that being lazy or being poor at organizing your own life, but essentially, one of the things that I really missed about doing coursework when I was doing research type work was the fact that my research was like not terribly structured in comparison to the coursework. It's like, you know, and, you know, this is also partially my own fault, and, you know, at this time in my life I was going through some things, but no, I didn't. I wouldn't say I had a particularly good time. It's like, I wouldn't say that I would, like, go back and do an undergraduate degree instead of a, like, if I had a choice between the two, I would choose an undergraduate degree. You do different things at different parts of your life, and, like, the grad work was the correct thing for me to be doing at the time in my life I was at when I was in grad school. But, like, it's no picnic. If you're considering doing grad school, understand it's no picnic, right? But yeah. Anyway, that's about as much answer as I can give you. Well, if there's nothing further, then I'm going to sign off here. Thank you very much for listening to this old codger yammering on about math for an hour. Take her easy.